Let us discuss problem 1.272. This says, when you form a smooth rod AB of mass m and length L rotates freely with angular velocity omega naught in a horizontal plane about a stationary vertical axis passing through its end. So I have this is axis and there is a horizontal rod. This rod is rotating about this axis. Mass of this rod is m, length of this rod is L, and angular velocity of this rod is omega naught. And this is kept on a smooth horizontal plane. So this is kept over a smooth horizontal plane. Are getting? The whole system is kept over a smooth horizontal plane. So this is a smooth plane. Now question says, a small sleeve of mass m starts sliding along the rod, and mass of this rod is capital M basically. So mass of the rod is capital M, and there is a sleeve of a small mass m. Initially this is kept at A and this is B. So initially sleeve is here. So there is a sleeve. Initially sleeve is kept at point A and mass of the sleeve is m. Find the velocity of the sleeve relative to the rod when it reaches to the end B. So we have to find V dash, that is the velocity of sleeve with respect to rod. Let us try to analyze what will happen. And this sleeve and rod are frictionless. Initially this sleeve is here, that is and A. After some time this rod is rotating, so this rod will be rotated by some angle theta, and this sleeve will go here. After some more time this rod will even rotate more angle, so you will have something like this, and the sleeve has reached here. After certain time this sleeve will reach to the end B. At that point of time we have to find what is the velocity of sleeve with respect to rod. Are you getting? Now what we are going to do is, we are going to apply angular momentum conservation in this case. So let us see this situation. In this case there is this sleeve and rod applying no force. So about this axis there is no force acting. So this means because this hinge is free hinge, no external force is acting, no external torque is acting about this axis. So this means angular momentum has to be conserved. So I can write angular momentum has to be conserved about an axis that is passing through A. Angular momentum is conserved. Now let us write initial angular momentum about A. So initially this rod is simply rotating with angular velocity omega naught, and this sleeve is here, so sleeve will have moment of inertia 0 because the distance from this axis is 0, so sleeve will have moment of inertia 0. So I will have only angular momentum of a rod, and that is ml square by 3, because moment of inertia of a rod about this end is ml square by 3, and I have to keep capital M. So this is ml square by 3 into omega naught. So this is my one equation. What will be the final angular momentum? So let us say when this sleeve reaches here, this is rotating with angular velocity omega. This means what is happening when this sleeve is going this side, the angular velocity of rod keeps decreasing. Why this is decreasing? because in this system there is nothing that provides the energy. So some of the kinetic energy of the rod gets converted into the kinetic energy of sleeve. So sleeve has some velocity v dash. Let us say v dash is the velocity of sleeve with respect to rod. Are you getting? So now, what is the total angular momentum this time? Once again, the rod will have angular momentum ml square by 3 into omega plus this sleeve. Now this sleeve will have two velocities. One velocity is v dash, another velocity is into r into omega, and this length is l. So I can write this side will have l into omega. Both velocity will be perpendicular because of this sleeve is also moving in a circular path. So this sleeve follows a circular path. I think all of you are able to understand. So due to this circular motion, there will be velocity L into omega. Now due to this velocity will not contribute to the angular momentum, but this velocity passes through the axis. So this will not contribute to the angular momentum. This velocity will contribute to the angular momentum. So I can say either I can think this velocity r cross mb in terms of r cross mb, or even I can simply think about this axis. This mass sleeve is moving in a circle with angular velocity omega. In that case, I have to write angular momentum I into omega. So I will be ml square and omega. So this is the final angular momentum. So I have to equate these two angular momentum, ml square by 3 into omega naught, that is the initial, so it will be final, ml square by 3 plus ml square into omega. So this is my equation number 3. From here I can get the value of omega. So L square goes out. So I will have omega is equals to m omega naught. And let us say 3 also goes out. So we will have m plus 3m. You can write in a better way. Omega is equals to m divided by m plus 3m into omega naught. So this is the angular velocity. But I want v dash. My final target is to find v dash. How will find this one? To find v dash, what we will do is we will apply energy conservation. So what is the initial energy? Initial kinetic energy, because there is no loss or gain of potential energy. So I will work only in terms of initial kinetic energy. We will have half I omega square, and simply rod is moving. So for rod I will have ml square by 3. This is a pure rotation about the end A, half I omega square, and omega at this point of time is omega naught. This is the initial kinetic energy. Final kinetic energy, I will have rod plus sleeve. For rod I will have half ml square by 3 into omega square plus, now I have to write kinetic energy for sleeve. Now sleeve basically has two velocity. You see, sleeve has, this is my sleeve, this has a velocity v dash, and this also has a velocity L omega. So what is the total velocity of sleeve? Either you can work in terms of half I omega square, or you work in terms of total velocity. That will give you the same thing. So if see, total velocity of sleeve will be total velocity of sleeve, that is the resultant of these two velocities. This is the velocity with respect to rod, and this is the velocity of sleeve again because of the circular motion. So you see, this sleeve has two velocity, this velocity plus this velocity. So this is with respect to rod, but rod is itself moving in a circular path. So this is the velocity of rod. Rod will have L omega velocity at the one end. So if you see, this rod will have, at this end rod will have L omega velocity. So I have to take the total velocity. So this is the velocity of sleeve with respect to rod, plus this is the velocity of rod with respect to ground. So total velocity of the vector sum of these two. So I will have simply V dash square plus L omega whole square under root. Are you getting? I need total kinetic energy. So let us plug the value in total kinetic energy. So half m V square I will have. V square is simply V dash square plus L square omega square. Are you getting? I think all of you are able to see this one. Now let us call this equation as 4, so the top equation, and let us call this equation as 5. So I have to equate 4 and 5. So energy conservation I can apply. So if I equate 4 and 5, so this is 4 is equals to 5. That energy has to be conserved, so I can write half ml square by 3 omega naught whole square. This is equals to, final is half ml square by 3. I think you are able to see this one. Omega square plus half m v dash whole square plus L square omega square. Now half you can cancel out throughout and take omega omega from one side, and you can also cancel if you want. So 3 to, so half goes throughout, 3 also goes, so 3 here, 3 here, I have to multiply 3 here, so I can write ml square omega naught whole square. This is equals to, I can multiply by 3 ml square omega square plus 3m b dash whole square plus 3m L square omega square. I think all of you are able to see this one. Now let us keep the omega square term once at one place. So ml square omega naught whole square, this is equals to omega square if I take common, ml square plus 3ml square plus 3m v dash whole square. Now I already know the value of omega, so you check your copy. So if you see, this omega is here, m by m plus 3m into omega naught. I can plug this value. Let us cancel L square term also. So I will have m omega naught whole square is equals to omega square m plus 3m plus 3m v dash whole square by L square, because I have divided by L square. Now plug the value of omega square. So I will have m omega naught whole square. Omega square is m by m plus 3m whole square into m plus 3m plus 3m v dash whole square by L square. Are you getting? Now m plus 3m cancels out, so I will have, this is also omega naught whole square, so omega naught is also there. So I will have m omega naught whole square is equal to, m plus 3m goes out, so I will have m square omega naught whole square divided by m plus 3m plus 3m b dash whole square L square. Now if I take this side, I will have m omega naught whole square common, 1 minus m by m plus 3m, and this is simply mathematics I am doing, there is no physics involved here, 3m v dash whole square L square. So this will be, m goes out, so we will have 3m into capital M, so 3 small m capital M omega naught whole square divided by m plus 3m is equals to 3m v dash whole square L square. So 3m cancels out, I think you are able to see this one. So from here I can write V dash. So V dash will be omega naught L square, so root over omega naught L. So that is simply omega naught L divided by under root m plus 3m. So this is the final velocity V dash of sleeve with respect to the rod. There will be a capital M also. So now see, this problem is a good problem. What are the important point we have in this question is, first important point we have, that is angular momentums of the system is conserved. If you see the vertical axis, there is no external torque that is acting because no any other forces that are acting. The sleeve and the rod are basically frictionless, so even that friction is absent. mg will basically not exert any torque in the z direction. So if you see, somebody can say about mg will also not exert any torque. So if you think about mg will basically not exist, so even mg is there. Now mg will not try to rotate in this direction. Mg will have a torque, but that torque will come in this direction. Let us say mg into this distance, and this torque will come in this direction. And my direction is this. I am conserving angular momentum in this direction. So this is my, let us say, z axis, this is y axis, this is x axis. So even there is a mg that is acting, mg will create a torque in the y direction. So even mg is not creating any torque in the y direction. So in the y direction, angular momentum will remain, in the z direction, angular momentum will remain conserved because there is no torque that is acting. And the second important point we have in this problem, that is the concept of relative motion. The rod itself is moving in a circular path, and over that rod the sleeve is moving in a straight line. So if you just sit on the rod and if you think and you see, the sleeve is moving in a straight line. So motion of a sleeve with respect to the rod is a straight line, simple. And that's why we have assumed the velocity with respect to rod is simply v dash. But the rod itself is moving in the angular circular path. Due to this straight velocity, due to the velocity v dash, sleeve will have no angular momentum. But due to circular motion, this will have angular momentum, and that is ml square into omega. Because v is passing through this axis, so r cross mv is 0, so angular momentum of v dash will be 0. Now next important point, when we are doing energy conservation, I have to take the total velocity of sleeve to write energy of sleeve. Sleeve has two velocity. One velocity is v dash away from the radius, that is in the radially outward direction, and it also has a velocity r into omega, that is L into omega in tangential direction. So sleeve has two velocity, one velocity with respect to rod and another velocity due to the speed of rod, so that is L omega and v dash. And of course, by chance these two velocities are perpendicular to each other. One is in the radial direction, other is in the tangential direction. If these two velocities are perpendicular to each other, I can find the resultant velocity easily, v1 square plus v2 square, or vx square plus vy square, or you can also say v radial square plus v tangential square. So now I know the total velocity of the sleeve. So I can easily write kinetic energy of sleeve plus kinetic energy of the rod, and I can equate with the initial kinetic energy of the system. One important point, in this situation, if you see this initial omega naught keep decreasing. Why this is happening? Because in this system there is nothing that keeps this omega naught constant. If there are some external agent that is moving this rod, in that case omega naught will remain constant. But in this case there is no external agent. You are simply in initial at t is equals to 0, you have given a velocity omega naught to the rod, and then you just leave the system. So you see, there is no external force that is acting, there is no external torque that is acting to keep the motion on to keep the omega naught constant, but there is nothing like that. So omega naught will keep decreasing because due to that sleeve is gaining the energy, sleeve is gaining the velocity. So this problem is quite good problem. We'll discuss the next problem.